In this video, we're learning about normal distributions. Sometimes they're called bell curves because it kind of looks like a bell. So previously we learned about some important statistics. So the mean is sort of the average, or it's a way to measure the center of the data, sort of the center. Median's technically right in the middle, but the mean should be roughly where the center of the data is. Standard deviation is how spread out the data is. So with these two, we can actually make predictions about probabilities. Now, it turns out that a lot of data will fall into this shape called the bell curve. That's something you can prove mathematically, but it's a bit beyond this video. Just trust me for now. A lot of things in the real world follow this shape. So for example, heights do. So the average height of an Australian woman is 161 centimeters. So we can put that right in the centimeter, right in the center. And then we're going to go up with standard deviations. So plus 7. So our next one will be 168. Our next one will be 175. And then our next one will be 180, 182. Just like that. We're going to go back in lots of 7. So 154, 147, and 140. Just like that. So you can sort of imagine for people to be less than 140 centimeters, that's going to be quite unlikely if you're an adult Australian woman. And then to be taller than 182 again is quite unlikely. And you can imagine that most people are sort of in this range, 154 to 168. In fact, that would be about 68% of people. So calculate the probability that they're between 161 and 168. So we can read it off as 34.13%. Now, really importantly, this is the percent when they ask for it, but the probability is different. Probabilities are between 0 and 1. So this is 0.3413 is the probability. Got to be really careful about that difference. Calculate the probability that an adult Australian woman is between 170 and 180. So previously we had the two numbers, 161 and 168. So we're very happy about that. We could just read it straight off the graph. But 170 is like there, and then 180 is like there. So I anticipate it's maybe about 12 or 13% based on those numbers, but we're not entirely sure. So this is where our calculator comes in handy. So we're going to jump into statistics here, just through that. And then we're going to go into dist and F1 for normal. We're going to use NCD. Now, if you've got it saying list here, you just hit F2 for var. So that's variable. We enter our lower and upper. So in this question, our lower is 170 and our upper is 180. And then we can enter our standard deviation, which is 7, and our mean, which is 161. So we just scroll down now and we're going to hit this to work out that probability. So it's 0.09, let's go 3 significant figures, 0960 would be 3 significant figures. Okay, we can also check our previous answer. So if I just change the lower to 161 and the upper to 168, then, jump back into that and then go all the way down, hit enter. You'll see 0.3413 is the probability there. Now, I've been a little bit cheeky here. The notation hasn't been fantastic, what I've done so far. So I'll just go and clean that up. Let X be the height of an Australian woman in centimeters. Then we say X squiggle N, so that means X is distributed normally, and then we give the mean and standard deviation. So the mean was 161 and the standard deviation was 7. And then the probability that X is in between 161 and 168 roughly equals the 0.3413. That's the number we worked out before. So that is your notation. Now, when you do a further part of this question, you don't need to write out that first bit again. We can just say here the probability that we're between 170 and 180 roughly equals that number there. Okay, next we want shorter than 154. So we can sort of read this off the diagram and add up those three numbers. Or we could sort of imagine that it's 50% to the left here. So it's 50 take 34.13. So if we want, we can actually work that out. So we'll just go into normal calculator, 50 take 34.13. So probability that x is less than 154. I guess the question says shorter than, so we're going to use a strict less than sign, but it doesn't really matter because the probability you're exactly 154 centimeters is actually 0. So we're just going to work that out, 0.1587. Now we can actually work this out using our normal CDF as well. So if we jump into stats again, and we're going to go dist, norm, NCD, keep the standard deviation and mean the same. My upper in this case would be 154. My lower, you might be tempted to write 0, but your calculator doesn't know that heights can't be negative. So your lower is actually minus, and then we're just going to do a whole bunch of 9s. Basically, that's our stand-in for minus infinity. We're going left forever. So we'll see what we get there. If we chuck that into the calculator, just scroll down and hit execute. So we get 0.1587 as well, which is good news. Okay, in a sample of 80, how many do we expect to be taller than 164? So probability that x is greater than 164 roughly equals. So we're going to jump back in. We're going to set our lower to 164, and our upper can be a whole bunch of 9s. And then we're going to go and execute that. So we got 0.3341. Now that's the probability. So it's about 33% will be over that. So out of 80 is 0.3341 times 80. That's how you work that out. So we can work out what that is. And we just do that by typing it into the calculator. Try and get as many decimal places as you can. So it's about 26.7. So 26.7. So it's about, because it's people, we'll give it in whole number. So 27 out of 80 are over 164 centimeters tall. Well, out of 80 expected to be over. Okay, so that's how we answer that question there. Now, the owner of a basketball team wants people in the top 15%. So this is where we use something called inverse normal. Basically, we're trying to work out probability that x is greater than some mystery number would be 0.15, 15%. So if we look on this diagram here, I'm expecting that maybe that mystery number is about there. And then everything to the right of that would add up to 15%. So something like that is the question I'm trying to answer. By the way, in case you're curious, these numbers, the probabilities are actually the area underneath the curve. So any big areas correspond to big probabilities. Okay, so how do we do this? Well, I'll just draw like a simplified diagram. So basically, I'm going to call this question mark, I'm just going to call it K. That's usually what people call it. And then I would like that the area is 0.15. So we can go back into our calculator, into stats, hit F5 for distribution, normal. You're hitting inverse normal this time, so it's F3. The tail is a right tail because we've drawn it on the right-hand side. And the area was 0.15. Standard deviation and mean is the same as before. And we should get 168.2. So K roughly equals 168.2 centimeters. By the way, in case you're curious, the area back here would actually be 0.85. So if I did this question using a left tail and 0.85 there, I should get the same answer, which I do. I'd encourage you to think about why these areas might have to add up to 1. Cool, so yeah, K is 168.2, so we could give this in like a sentence answer. So the shortest height allowed into the basketball team is 168.2 centimeters. Not the best strategy for making a basketball team, but anyone higher than that number will be in the top 15% of heights.